Nucleus of an atom. The central part of an atom is called the nucleus. It is composed of protons and neutrons. Protons and neutrons together are called as nucleons. Generally, we indicate the protons with the letter Z, and this is called the atomic number. Z is called atomic number. It indicates the number of protons. In a neutral atom, the number of electrons is also equal to the number of protons. So Z can indicate the electrons in a neutral atom. Let us indicate the number of neutrons by capital N. Capital A indicates the mass number of this nucleus. So A is equal to Z plus N. Let us recollect the symbol used for nucleus. It will be generally atom or nucleus. Sometimes it will be represented, it will be used for nucleus as well as for atom. If X is an element, Z atomic number, A mass number, so we generally write the symbol as X as left suffix Z, right superfix A, or left suffix and superfix ZA. XZA is the symbol for the nucleus or sometimes for atom. X represents the element, Z represents atomic number, A represents mass number. Let us take an example. If we take lithium atom, it consists of 4 neutrons and 3 protons. In the nucleus, there are 4 neutrons and 3 protons. So the mass number is 7 and the proton number is 3. So Z is 3 and A is 7. So it will be written as Li 37, suffix and superfix. 3 is suffix and 7 is superfix. Like this we represent nuclear size. The size of the nucleus is of the order of 10 to the power of minus 14 meters. 10 to the power of minus 14 meters. We adopt a new smaller unit to measure such small distances like the size of the nucleus. That is Fermi. 1 Fermi is 10 to the power of minus 15 meters. This is the small unit that is used to measure the size of the nucleus. It is noticed that the volume of the nucleus is proportional to the mass number. It was noticed that the volume of the nucleus is proportional to the mass number. If we represent the mass number by A and volume by V and the radius of the nucleus as capital R, then we can write V is proportional to A because volume is found to be proportional to mass number. But volume is 4 by 3 pi r cube. Therefore, 4 by 3 pi r cube is proportional to A. Considering the nucleus is of the order of, it is of the shape sphere, considering the spherical shape of the nucleus. From this relation, we can write the relation for radius as r0 into a to the power of 1 by 3. Replacing this proportionality with a constant, we can write the relation for radius as r is equal to r0 into a to the power of 1 by 3, where the value of r0 is approximately 1.1 into 10 to the power of minus 15 meters. Remember that it is approximate value. r0 is equal to 1.1 into 10 to the power of minus 15 meters. So this is the relation that is used to measure the size of the nucleus. R is equal to r0 into a to the power of 1 by 3. Mass of the nucleus. We measure the mass of the nucleus with an unit called atomic mass unit. Atomic mass unit. We consider the mass of carbon 612 as 12 atomic mass units. We assign 12 atomic mass units as the mass of carbon 612 atom. So we get the value of one atomic mass unit as 1.66054021 into 10 to the power of minus 27 kgs. One atomic mass unit is equal to 1.66054021 into 10 to the power of minus 27 kgs. Its value in terms of energy is given as 931.54 MeV. One atomic mass unit is equal to 931.54 MeV. MeV is million electron volts. 1 electron volt is 10 to the power of 1.6 into 10 to the power of minus 19 joules. 1 MeV is 10 to the power of 6 electron volts. 1 million electron volt is 10 to the power of 6 electron volts. 1 electron volt is 1.6 into 10 to the power of minus 19 joules. The mass of a proton is 1.007277 atomic mass units. Mass of proton is 1.007277 atomic mass units, and that of neutron is 1.008665 atomic mass units. So mass of neutron is slightly greater than the mass of proton. Proton is 1846 times heavier than electron. Nuclear forces. Nuclear forces. Protons are positively charged particles. So the protons in the nucleus should fly apart because of repulsive force between them. But it is not happening. So there must be a strong force, attractive force, which dominates this repulsive force. That force is identified to be the force between nucleons, and it is known as nuclear force. The relative strengths of the forces, that is gravitational force, electrostatic force and nuclear force, is given as 1 is to 10 to the power of 36 is to 10 to the power of 38. That is, electrostatic force is 10 to the power of 36 times stronger than gravitational force, and nuclear force is 10 to the power of 38 times stronger than gravitational force. So compared to electrostatic force, this nuclear force is about 100 times stronger, and this force is an attractive force, and it acts between any two nucleons, that is between two protons, between two neutrons, and between a proton and a neutron. The magnitude of the force between two protons is same as the magnitude of force between two neutrons, and it is the same as the force between a proton and a neutron. So the magnitude of force is the same between any two nucleons. Properties of nuclear forces. Nuclear forces are attractive forces. They are very strong forces in nature. They are charge independent. That is, the quantum of force is the same between any two nucleons. They are short range forces. That means they are applicable within a small distance of the order of 1 Fermi. They are spin dependent. The force is maximum if the spins are parallel. They are non-central forces. They do not act along the line joining the centers of the nucleons. They are saturated forces. Each nucleon attracts only their nearest neighbors. They are exchange forces. That means they arise as a result of exchange of pi mesons between nucleons. These are the properties of nuclear forces. They are attractive forces, strong forces, spin independent, and short range forces. They are spin dependent, they are non-central forces, saturated forces, and they are exchange forces. Mass defect. Now we are going to study one of the properties, mass defect. We know that there are protons and neutrons in the nucleus of an atom. If we consider the sum of the masses of protons and neutrons, the total mass of the protons and neutrons present in a nucleus, that mass is greater than the nucleus formed by them. When they are independent particles, their mass will be more, but when they form a nucleus, then the mass of the nucleus will be less. So some mass is disappearing when these particles are formed into the nucleus. The difference in the mass of the nucleus and the mass of the nucleons is known as mass defect. The difference in mass of the independent particles and the mass of the nucleus which they form is termed as mass defect. Let us have a mathematical idea of mass defect. Let us represent the mass of the nucleus of an element XZA with capital M. Mass of the nucleus is taken as capital M. Mass of proton MP. Mass of neutron Mn. Then the mass of the nucleons is Z into MP, because there will be Z protons, plus A minus Z into Mn, because A minus Z is the number of neutrons. So ZMP plus A minus Z Mn represents the mass of the nucleons. And the mass of the nucleus is taken as capital M. Therefore, the mass defect delta M is equal to ZMP plus A minus Z into Mn minus capital M. The mass defect per nucleon is termed as packing fraction. Mass defect is delta M and mass of the nucleus is capital A. Therefore, packing fraction is delta M by capital A. Mass defect divided by mass of the nucleus. Let us take an example. For example, let us take lithium nucleus. The mass of the lithium nucleus is 7.016005 atomic mass units. There are 3 protons. So mass of 3 protons is 3 into 1.007277. That is equal to 3.021831 atomic mass units. There are 4 neutrons inside the nucleus. So mass of the 4 neutrons is 4 into 1.008665. That is equal to 4.034660. So by computing we will get the mass defect as 0.040486 atomic mass units. Binding energy. We know some mass disappears when nucleons they form into a nucleus. The decrease in mass is called as mass defect, and we can estimate the energy equivalent to this mass defect from Einstein's relation E is equal to mc square. This energy appears as though it is binding the nucleons. So it is called binding energy. So the energy which is equivalent to the mass defect is called as binding energy. We can define this as the minimum energy required to split the nucleus into its constituent nucleons. Because by giving same amount of energy to the nucleus, the nucleons get separated. So we can define this as binding energy as the minimum energy required to split the nucleus into its constituent nucleons. We define another term, binding fraction, which is binding energy per nucleon. Binding energy per nucleon is termed as binding fraction. If delta E is the binding energy, delta E divided by A gives binding fraction. We have calculated the mass defect of lithium nucleus as 0.040486 atomic mass units. So the binding energy is 0.040486 into 931.54 MeV, which comes out to be 37.713 MeV. In lithium atom, in lithium nucleus, there are 7 nucleons. So the binding fraction is 37.713 divided by 7, that is equal to 5.387 MeV. Like this we can calculate the binding energy and binding fraction. Study of binding fraction. Study of binding fraction is very useful in assessing the relative strengths of the nuclei of different elements. To study the stability of the nuclei of different elements, binding fraction is highly useful. To study this relative stability, we draw a curve between mass number on x-axis and binding fraction on y-axis. We plot mass on x-axis and binding fraction on y-axis. When we draw a curve for all the natural elements, we get a curve of the shape shown in the figure. Notice the graph. It starts with 1H2, isotope of hydrogen, and for helium, lithium, carbon, nitrogen, oxygen, iron, uranium, these atoms, they are placed at their relative positions. We notice that the binding fraction increases with the atomic mass number. Of course, there are slight variations. When we see helium is having more binding fraction compared to lithium, like that there are some variations. But we notice that the binding fraction will increase with the increase in mass number, and it will reach the maximum value around iron, not exactly at iron, but around iron. And it is fairly constant. It will have a high value for elements around iron. For some elements around iron, it has got highest value. So these nuclei are more stable. For heavier elements, higher than this iron. For heavier elements, as we go for higher and higher elements, we notice that the binding fraction decreases. So uranium, the highest element, natural element, will have less binding energy compared to iron. Uranium has got less binding fraction, not binding energy. Binding energy is of course more, but binding fraction of uranium is less than that of binding fraction of iron. On the basis of the relative values of binding fraction for different elements, we can draw the following conclusions. Light nuclei and heavy nuclei can be transformed very easily. We notice that the binding fraction of lighter nuclei and heavy nuclei is far less compared to the intermediate nuclei like iron. Compared to iron, uranium and other elements like carbon, they have less binding fraction. So we can conclude that these nuclei can be transformed very easily than iron nuclei. Less binding fraction for hydrogen and lithium compared to helium indicates the existence of shell model of energy levels of the nucleus. The existence of shell model of energy levels in the nucleus can be imagined because of the less binding fraction for hydrogen and lithium compared to helium. The nucleus can also undergo excited states. It can also occupy higher energy levels like an atom. So it can also be excited. The nucleus can also be excited, like the atom. In an atom, the energy required for excitation is only in electron volts, very small energy. But in the case of nucleus, the energy required will be very, very high. It will be in million electron volts. The excitation energy of nucleus will be in million electron volts, whereas the excitation energy of the atom is only in electron volts. Due to the de-excitation of atom, photons are emitted. Less energetic photons are emitted. Due to de-excitation of atoms, less energetic photons are released. But in case of nuclear de-excitation, the energy is very high. It is so high that that gamma radiation is emitted. Highly energetic gamma radiation is emitted from the nucleus due to its de-excitation.